All right. Okay, so I think that I have started my live stream. I'm just going to double check on another device to make sure that it is streaming live. Okay, so now that I know that this is working, I'm going to get started. So this is a live review session for kinetics and equilibrium. And I'm hoping in this hour to take you through some topics in kinetics and equilibrium that will help you to review for the Regents exam. I am Mrs. T. My name is Elizabeth Tuminello. I'm a chemistry teacher at Calhoun High School in Merrick, New York, and I hope that I'm able to help you a little bit today with kinetics and equilibrium. If you would like to text in questions to be answered during this review session, you can text at 7DFAB to the number 81010. If you've never joined a Remind group before, it's going to take you through a few steps of just saying what your name is. And what I'm going to do, I actually have it set on Remind to send out a few messages during the broadcast that you could just reply to if you needed to. So give you a second to do that. If you want to text at 7DFAB to 81010, that will allow you to join the Remind group. And at intervals during the video, Remind messages will go out, and all you have to do is respond to the Remind messages in order to ask questions during the video. And that's just in case the the chat is not up. And I'm looking on my screen on a different screen, and I don't see any chat and I don't see any comments. So I think you're going to have to use the Remind group. So when we talk about kinetics, if we're going to define kinetics, kinetics studies rates and mechanisms of reaction. And in order to know what we're talking about when we're studying rates and mechanisms, we need to know what a rate is and we need to know what a mechanism is. So a rate talks about how fast or slow a reaction is going. So we can measure how fast or slow a reaction is going by saying how many moles of reactants are consumed, sorry about my sloppy line there, or by saying how many moles of product are produced or made per unit of time. So just like a rate of speed, we're going to be measuring the rates in kinetics based on the amounts of reactants that are consumed or the amounts of products that are made. Now, a mechanism, on the other hand, has to do with the steps. So every reaction involves a series of steps in order to get it to happen. And it's also sometimes called a pathway. So the steps that a reaction takes will dictate how much energy the reaction requires. And those steps will also dictate how fast or slow a reaction is going to go. So rates and mechanisms are two pieces of information that we need to know to talk about kinetics, and they are interrelated. We talk about collision theory. Collision theory tells us that in order for a reaction to happen, the particles that are going to react have to hit each other. So these are either molecules or atoms or ions. They're going to have to hit each other. And just hitting each other isn't enough in order to cause a chemical reaction to happen. These molecules have to actually hit each other with specific criteria. They have to hit with enough energy, and this energy that they need to have is called activation energy. And they need to hit with proper orientation, which basically means that they have to hit in the right spot. Maybe only one surface of an atom or a molecule or an ion is available or is where this bond will form or how the bond will break. And so the molecules, ions, or atoms or species have to hit in the right spot with the right amount of activation energy in order for this reaction to happen. Now, any factor that we can use to increase the number of effective collisions will make any reaction go faster. And so the next piece that I'm going to talk about are those factors that we can use in order to speed up or slow down a chemical reaction. And so the factors that affect the rate of reaction are going to be temperature, concentration, surface area, catalyst, and nature. We can manipulate different factors for a chemical reaction in order to make it go faster or slower. Most of the time, we're concerned with making it go faster. And when we talk about these 5 factors, I'm going to break down each of the factors individually now. So when we talk about temperature, it's very important not to forget that temperature is going to measure the average kinetic energy. So this is related to speed, but it's not directly going to tell us speed if we're talking about 2 different substances. But we're going to be measuring the average kinetic energy with temperature. Some particles in a sample might have a slightly higher kinetic energy. Some particles might have a lower kinetic energy, but the temperature measures that average. Increasing the temperature will increase the rate of reaction by increasing the number of effective collisions for 2 reasons. Because higher temperature means faster speed. Faster speed means that the particles will actually bump into each other more often. We will have a greater number of collisions. Faster speed also will cause more of the collisions to happen between particles and more of those collisions to have enough energy. So they're going to be hitting each other more often, and they're going to be hitting each other harder because they're moving faster. These 2 pieces will lead to an increase in the number of effective collisions at a higher temperature, which means that at a higher temperature, we can make reactions go faster. Concentration. First of all, only gaseous substances and aqueous solutions can experience a change in concentration. Remember, we cannot change a concentration for a liquid or a solid. But increasing the concentration of a gas or increasing the concentration of an aqueous solution will increase the rate of a chemical reaction. The reacting particles will actually be closer together. There'll be less space between them, so they'll actually have to collide more often. Now, having more collisions per unit of time will make more of those, will increase the number of effective collisions, and anything that can increase the number of effective collisions will cause the reaction to speed up. We talk about surface area. Surface area is going to be higher in a powder. We will have, oops, sorry about that. We will have a higher surface area if we're talking about a powder than a solid. Remember that a solid block, if we have a solid block, we have parts on the inside that are not exposed, and those parts on the inside that are not exposed would not be available to collide. So when we talk about surface area, increasing the surface area would be making it into a powder. Decreasing the surface area would be using just a plain solid block. When we talk about this surface area, increasing the surface area will speed up a reaction involving solids because more areas will be exposed for collision. Whereas before, if you had a solid block before, the ions or atoms or molecules on the inside are not exposed to collision. So powder always reacts faster than a solid block or a solid hunk of a solid. If we talk about a catalyst will cause a reaction to take an alternate pathway. So if we have the presence of a catalyst, the reaction will actually take an alternate pathway. So we'll take different steps in the reaction when a catalyst is present than when a catalyst is not present. These other steps, this alternate pathway, will actually have a lower activation energy with the catalyst than the pathway without the catalyst. This means that more of the collisions will be considered effective collisions because the collisions will actually need less energy on collision. So the presence of a catalyst will speed up a reaction. Now, a side note about catalysts, because this chapter also talks about equilibrium, if we add a catalyst, we do not have a shift in the equilibrium. Both the forward and the reverse reactions will be sped up equally when we're talking, when we add a catalyst. So since the forward and the reverse will both be sped up equally, that means that they'll both be going faster, but they'll still be in the same rate as each other. So adding a catalyst does not shift the equilibrium in terms of Le Chatelier's principle. We talk about the nature. This is actually something that for a particular set of reactants, we can't change their nature, but some reactants happen to move, some reactions will happen faster based on the types of reactants involved in the reaction. It's just based on how the reactants are put together. We know that organic reactions tend to happen very slowly, and that's because they tend to have very high activation energies. Their bonds are very strong, and so they have very high activation energies in order to start those reactions. So organic reactions tend to be really slow. Whereas ionic reactions in solution tend to happen very quickly, and that's because the ions are not connected to each other in solution. They move freely, and so they are more available to collide. We don't have to overcome their attraction for each other before they can become part of a new reaction. When we talk about heat of reaction, that would be our next topic here. Heat of reaction is our delta H. So this H for delta H, or sometimes they also call this the enthalpy of reaction. We usually use the word enthalpy and the word heat pretty interchangeably. When you talk about enthalpy or heat, you're also usually talking about kilojoules or joules. So these are going to be, oops, I didn't mean to move that. These are going to be our two units that will be most closely associated with these heats of reaction or enthalpies of reaction. So when we're talking about our heat of reaction or enthalpy of reaction, it's always going to be the heat of the products minus the heat of the reactants. So I'm going to be talking about potential energy diagrams in a little bit, but we're talking about, remember that we always start here. Our reactants have some amount of energy, some amount of heat, some amount of thermal energy. And we go through a series of energy changes in order to form products. In between, we have our activated. And the difference between the heat content of the products and the heat content of the reactants gives us our delta H. Now this one happens to be endothermic because the energy of the reactants increases overall as products are formed. Remember that exothermic will start high and end low. I do have some more slides on endothermic versus exothermic, so I'm not going to put that right here. But again, we're always going to do the heat content of the products minus the heat content of the reactants, which means that for an endothermic reaction, the products are higher, so we're going to get a positive number for the delta H. For exothermic, the products are lower, so we're going to get a negative value for the delta H. And now there's actually on table I, we have a key that tells us that the negative sign for delta H indicates an exothermic reaction. If we look here, table I is heats of reaction at 101.3 kPa and 298 Kelvin, and there is an asterisk here. And if we go down to the bottom and we look at the asterisks, it says the delta H values are based on molar quantities represented in the equations, which I'll explain in a second, but it also says a minus sign indicates an exothermic reaction. So they're telling you, without you having to remember on the reference table, that negative delta H is going to mean that you have an exothermic reaction. So now what does it mean that the delta H values are based on molar quantities? If I pick just one reaction, for example, let's just pick the very top one, you will give off 890.4 kilojoules if you have 1 mole of methane reacting with 2 moles of oxygen, making 1 mole of carbon dioxide and 2 moles of water. But if we use 2 moles of methane, because that is double the coefficient in the reaction, we would give off 2 times the amount of heat. So for each of these reactions, the amount of heat given off or taken in is proportional to the coefficients. If you double a coefficient, you double the heat. If you divide a coefficient by a number, you divide the heat by the same number, because they will always be proportional to the number of moles. If we look at it, for example, an exothermic reaction, this reaction has reactants that start high and products that end low. I always use, if you can write in cursive, the word Fox. If you put an axis before you cross your X around the X in the word Fox, ox, box, lox, it has to be something with an OX, you get your shape of your exothermic curve, right? That would be an X. If we also look at exothermic, we also know that heat is exiting overall. Heat is being given off overall. Because heat exits in an exothermic reaction, energy is in the product when written in the reaction. The value for the delta H will be negative, but we will add that amount to the products. So if the delta H on table I is, for example, like the one we were looking at, negative 890.4, we wouldn't write negative 890.4 as the energy. We would add 890.4 kilojoules to the product side. The negative sign just tells us that it is released. We do not put that negative sign in the reaction when we write it down, when we write the equation for the reaction. When we're looking at the potential energy diagram, the potential energy diagram will usually, when you see it with values, usually have dashed lines that are even with the reactants, the activated complex, and the products. My axis kind of didn't all show up there. So when we have these dashed lines, we have certain values that we usually need to know the location of. And those values are going to be potential energy values and activation energy values, and then of course our delta H. And hold on, I'm getting a message. Positive delta H, positive delta S, not spontaneous Y. I will keep that question in mind for when I get to my spontaneous reactions, and I will go over that one then. Now, when we are talking about this particular potential energy diagram, we are going to have 3 types of values that will reach the x-axis. So if a value on a potential energy diagram reaches the x-axis, that's going to be measuring the potential energy. If it goes from the x-axis to the reactants, it is the potential energy of the reactants. So in this case, my letter A is the potential energy of the reactants. My B here goes from the x-axis up to the activated complex, so that is going to measure the potential energy of the activated complex. C is going from the x-axis to the products, and so that is the potential energy of the products. Now, we have 2 values that start above the graph and go to the top, above the graph and go to the top, that would be what I'm going to label D and E. Above the reactants to the top is the forward activation energy, and RG energy, and E will be the reverse activation energy. And then finally, we will have a value that goes between the reactants line and the products line, and that will be our delta H. This delta H can go anywhere in this section in the middle as long as it's between the reactants and the products. Also, please don't forget that any of these values could slide from left to right. It's just a matter of which line they are above and which line they are below. So make sure you not only look, that you don't just look to see whether it goes to the x-axis or goes above the graph or goes between two values, but which two values you are actually going between in order to determine which type of value it's measuring. If we look at an endothermic value or an endothermic potential energy diagram, remember this is going to have a positive delta H. The reactants will be lower than the products, and the delta H will be a positive sign. So whatever value for delta H we see on table I, that value will be added to the reactant side to show that that energy is being taken in. Now, the values would be the same on here. Anything that hits the x-axis and goes to the reactants would be potential energy of the reactants. X-axis up to the activated complex would be potential energy of the activated complex. X-axis up to the products would be potential energy of the products. Reactants to the top would be forward activation energy. Products to the top would be reverse activation energy. And between reactants and products would be the delta H. Just went through all of that. I meant to do that on this diagram, so I'm just going to move forward and just say that if we do add a catalyst, this also is an endothermic value or an endothermic graph because we are going up from reactants to products. If we were to add a catalyst, remember just the height of the activated complex would change. The position of the reactants and the position of the products would not change. So what that means is that the potential energy of the reactants, the potential energy of the products, and the delta H would not change in the presence of a catalyst. There are three values that would change in the presence of a catalyst: the potential energy of the activated complex would change, the forward activation energy, and the reverse activation energy. These are the values that would change when you add a catalyst. When we look at our potential energy diagram, I had a great student teacher a couple of years ago who taught me this, that the delta H is like a hamburger. H is, hold on, I'm losing my mouse. Here we go. H for delta H, H for hamburger. And if you look at your potential energy diagram, you can separate it into a bottom bun, a top bun, and hold on, this is a little sloppy right here. I just want to fix this. Your delta hamburger. And if you look at the top bun, right here we have bun, we have bun. The central section here, this delta hamburger, we could put the arrow for the delta H anywhere in that central section, and that would be my delta hamburger, also known as my delta H. PE diagram with the catalyst again, the reactants stay in the same place, the products stay in the same place. We're only going to experience a decrease in the activation energy for the forward and the activation energy for the reverse because of the fact that we will have a change in the potential energy of the activated complex because of a new pathway being taken. When we talk about systems in nature, this goes back to a question that someone just asked. Someone actually just asked, does calorimetry or stoichiometry come into place anywhere in this topic? The only place where stoichiometry comes into play is the table I questions, where you have to change, if you change the coefficient of something, you will also multiply or divide the heat based on how you've changed the coefficient. Calorimetry does not come into play in my teaching of kinetics and equilibrium. I don't know if people use heat given off for a reaction and then use that heat in Q equals mc delta T. You certainly could do that, but that it would be outside the scope of the Regents chemistry curriculum. I do have another question from someone on Remind that's going to come into play here. Hold on, just finding it. And it was positive delta H, positive delta S, and about negative delta H, negative delta S, and whether or not these reactions are going to be spontaneous. So when we talk about spontaneous reactions, the way the Regents generally talks about this would be systems in nature, and using the formula delta G equals delta H minus T delta S, although some of your teachers may have taught it as part of your chemistry curriculum, this is not in the Regents curriculum. However, if you want to explain whether a reaction or predict whether a reaction will be spontaneous based on systems in nature tending to go to lower energy and higher entropy. First of all, remember, lower entropy means that exothermic is favorable. Higher entropy means that making more disorder is also favorable for a reaction. Lowering the energy would be through an exothermic reaction. Making higher entropy would be increasing the amount of gas, going from solid to aqueous, and decomposition, anything that increases the number of moles. So the way that I generally teach this to figure out whether a reaction will be spontaneous or not, which again, in the Regents curriculum lately, they've been calling this systems in nature. So when they say systems in nature, you have to think the word spontaneous. So when they say systems in nature, and you realize that they're talking about spontaneous reactions, you can have your delta H and you can have your entropy, right, which is your delta S. If delta H is negative, remember that's exo, that's good. If delta S is positive, remember that's increasing the entropy. Those are two favorable conditions. This reaction will be spontaneous. Two happy faces means definitely spontaneous. If you have a positive delta H, which is endo, and you have a negative delta S, which decreases the entropy, these are unfavorable. Neither of those is favorable in terms of their conditions. So this will never be spontaneous. If you have one happy face and one sad face, so if you have one favorable condition and one unfavorable condition, it's not going to definitely be spontaneous or not. It's going to depend on the temperature. So this is answering a question. Let me find where my remind is here. This is answering a question from Caitlin S. So Caitlin S., I'm answering a question right now. Definitely spontaneous would be two favorable conditions. Exothermic, increasing the entropy, would definitely be spontaneous. Definitely not spontaneous would be the opposite of that, which is endo and becoming more organized. So I'm just going to clear this so I can write again. So now if we have these two situations, which remember delta H is about the endo or exo, and delta S, delta S is about the entropy change, for those of you whose teachers didn't teach you about the symbol S. If you now have exothermic, right, which is a negative delta H, and decreasing entropy, which is a negative delta S. Negative delta H is favorable, but decreasing the entropy is unfavorable. This question, you can't, this particular set of circumstances, you can't tell whether it's spontaneous. It might be. We don't know. It depends on the temperature. That also goes for endo and increasing the entropy. These would, endothermic is not favorable thermodynamically, but increasing the entropy is. This one would also possibly be spontaneous, but it would depend on the temperature. This one would be spontaneous at high temperatures. This one would be spontaneous at low temperatures. But again, that's beyond the scope of the Regents course. You don't need to know that part. You just need to know that when it doesn't follow both favorable conditions, if it follows one, it might be spontaneous at certain temperatures. If it follows neither, it's definitely not spontaneous at any temperature. Okay, so Mohammed K just asked about whether or not how do you know whether a reaction is spontaneous? We just covered that. Hopefully, Mohammed, you put that question in before you saw that. That will be coming up, or you can rewind to find that. There was a question about ice melting in water, if it's exothermic or endothermic. That is not technically in this topic, but I'll answer it. Ice melting is on the heating curve. Anything on the heating curve is endothermic. Let's see what else we have. And then the other question that Mohammed K had was regarding equilibrium. I'm going to get into equilibrium right now. So I will be talking about the shifting of equilibrium in terms of Le Chatelier's principle in the next couple of slides. So if you have any further questions on those, please continue to respond or reply to those reminds. For those of you who didn't get to join the Remind group, if you text at 7DFAB to 81010, you can join the Remind group for this stream. And in about 10 or 15 minutes, another Remind message will go out. In fact, maybe I'll just push another one out right now, so that if you do join that Remind group, you are able to send me messages. All you'll have to do, if you do join the Remind group, all you'll have to do is just respond to the messages that I sent out that just say, respond to this message if you have any questions. So I'm just going to copy that and repeat the announcement, so that this way, if you just joined, you can have the opportunity to, oops, that's the wrong one. You can have the opportunity to send me a message. There we go. So that message will be coming out in about 2 or 3 minutes. Just want to give everybody a chance because of the time lag. And so what'll happen is you'll get the message, you'll get the Remind message, and you can just respond to it if you have any questions at all. Okay. So when we're talking about equilibrium, equilibrium is a situation where a system can reach a state of this dynamic equilibrium if there is a reversible reaction. Remember, equilibrium is always dynamic. It doesn't mean that the reaction stops. The reaction does not stop. It continues going in the forward and reverse direction, but it goes in the forward and reverse direction at equal rates. And since those rates are equal, we wind up having constant concentrations. So this, again, equal rates and constant concentrations. Okay, so I'm gonna go back for a second. Julia T said, I'm confused on how solid liquid gas is increasing entropy, because I thought that solid liquid gas is an endothermic reaction. And I'm just gonna go back, because that's actually a really big question that people tend to have. Entropy and enthalpy, exothermic, endothermic, delta H, and entropy, delta S, these are not dependent on each other. Okay, so what happens is you can have exothermic reaction independent of increasing or decreasing entropy. So one does not influence the other. So a reaction, exothermic or endothermic, is determined only by the delta H. Increasing and decreasing entropy is only determined based on whether we're going from solid to liquid to gas, going from a solid to a mixture, or increasing the number of moles of molecules or atoms by decomposition. So they are not dependent on each other. In fact, they are two completely separate concepts. I do often find that they are linked. People get them linked and mixed up in their head. But they are, just because something is endothermic doesn't mean that it can't also increase the entropy. They're two separate concepts. So back to equilibrium. We have equal rates and constant concentrations. The reaction does not stop. Someone had asked in the pre-questions about how to know something about equilibrium when it came to voltaic cells. Voltaic cells, when the voltage reaches 0, when your battery dies, that doesn't mean, oops, that's supposed to say reaches. When the voltage reaches, it has reached equilibrium. Sorry, now I'm making it even worse. When a voltaic cell reaches 0 voltage, it has reached equilibrium. It doesn't mean that the battery or the reaction has stopped. Remember that phase equilibrium would be the phase changes on the heating curve or the cooling curve, and solution equilibrium would be like if you look at table G, which looks something like this with all these lines all over the place. Any saturated solution on table G would also be considered to be at equilibrium. We talk about Le Chatelier's principle. Le Chatelier's principle says that a system in equilibrium that is subjected to a stress will shift in order to relieve that stress. So I did have a number of questions from people from people who either ask the questions in advance or ask the questions on Remind. What does it mean when a system will shift? Okay, so when we have a system shifting, remember, first of all, let's go backwards. When we're at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. If we shift, that means that the reactions are not at equal rates for a small period of time until a new equilibrium position has been reached. Now that's a lot of words that are kind of confusing. So what does that mean? That means that we might be going faster in one direction than the other for a short period of time. If we're going faster forward, we call that shifting to the right because we're making more products on the right than we are replacing those products by going to the left. If we are going faster for a time in the reverse direction than we are in the forward direction, that would mean that we are shifting to the left because we're building up reactants on the left without turning around and making them back into products on the right as quickly. Eventually, we will reach a new equilibrium where they're going at equal rates, but whatever we've built up, whether it's products on the right or reactants on the left, that amount will be different than it was before the shift. So the general rules that I use are add away, take towards, increasing pressure, shift to the side with less moles of gas. Add away means if you add a reactant, you shift towards the product. If you add a product, you shift towards the reactants. And this is because of collision theory. Increasing concentration of reactants or products will, you have those reactants or products used up in their reactions that they participate in. Take towards, if you remove something from a reactant or you remove something from a product, what that's going to mean is that you'll actually be going slower in the direction where that is a reactant, and that means that the opposite reaction is going faster for a short period of time. Increasing pressure shifts to the side with less gas. You count up the moles of gas on each side. Increasing pressure shifts to whichever side has less. For example, what I always start with is I look at my arrow and I always first say, okay, which side is the left? and which side is the right. If I increase the concentration of CH4, CH4 is on the left, and according to add away, because the CH4 reactant concentration is increasing, it has more effective collisions with the oxygen, so it's forming more products, we are going to shift to the right. That means that we are going to increase the number of moles of CO2, increase the number of moles of H2O, but we're not going to experience a change in concentration of the H2O because it's a liquid. We will also, in the process, we will use up oxygen in order to shift to the right, so the number of moles of oxygen will decrease. If we increase the temperature, we will favor the endothermic direction, and the endothermic direction is forward, so we're going to shift to the right. And again, shifting to the right means we're going to make more products by using up reactants. Effective increasing pressure, we need to count up the number of moles of gas on each side. 2 plus an understood 1. That means my left has 3 moles of gas, and this is just an understood 1. That means that my right has 1 mole of gas. So increasing pressure will shift to the right because that's the side with less moles of gas. So I will increase the amount of CO2 and I will decrease the amount of CH4 and decrease the amount of O2. If I increase the concentration of CO2, that's add away again. So increasing CO2 will shift away, will shift left. Shifting to the left means that the concentrations and the number of moles of everything on the left increases. The numbers of moles of everything on the right will decrease. Same problem, just more questions about it. If I add liquid water, there will be no change because solids and liquids will not affect, you cannot change the concentration of solids and liquids. I'm sorry, a question just came in about the last slide, so I'm just going to go back for a second. Someone asked, we have Julia T asking if the right side also has 3 moles of gas. No, we're not counting up moles of everything. We're just counting up moles of gas when we're talking about pressure shifting. So the H2O liquid does not come into play when we're counting up those moles for the shifting of pressure. It's only the moles of the substances that are gases. So hopefully, Julia T, that answered your question. Again, if we go back to what we were doing here, the effect of removing oxygen gas, that's take towards. So removing oxygen will shift to the left, means that we increase the species on the left, decrease the concentration of the species on the right. Again, we can't change the concentration of the water because it's a liquid. We can change its number of moles, but we can't change its concentration. And the effect of decreasing temperature, that's take towards. We're removing heat by lowering the temperature. So if we're removing heat, we're going to shift to the left, means that we will increase the species, the number of moles of species, what's on the left, and decrease the number of moles of what's on the right. The effect of adding a catalyst on any system in equilibrium is no shift, because what we have, or what we will have, is we'll have 2 reactions that are going at the same rate already. And all we do is speed them both up by the same amount. So by lowering the activation energy with a catalyst, we speed up both the forward and the reverse, but by speeding them up by the same amount, they're still at equilibrium. There is no shift in the equilibrium. Not all reactions can reach a state of dynamic equilibrium. We do have some systems or some situations that will not allow a reaction to go in both directions. So when a reaction goes to completion, it goes in one direction only. And you remember you have to have a reversible reaction in order to be able to reach equilibrium. So the types of reactions that go to completion is when we have one product as a gas and no other gases, and those gases will escape. And if those gases escape, they're not available to go in the reverse direction. So if they can't go in the reverse direction, we can't reach equal rates of forward and reverse, and we can't reach equilibrium. If we have a reaction where there's all ionic substances and one of those products is liquid water, that takes the ions out of the reaction, makes it impossible for those ions to, not impossible, makes it so that those ions are not available to react. Again, making it so that the reaction can only go in one direction. And if the reaction can only go in one direction, we can't reach equilibrium. And then finally, a lot of times this is in double replacement. If one product is a solid, which we would call precipitation, but we have all aqueous reactants, then that solid is not available to go in the reverse direction, and not being available to react in both directions would mean that they cannot reach equilibrium. So that was the end of my prepared PowerPoint. So what I'm going to do is I'm just going to put the whiteboard up. I'm just going to wait and see if any more messages come in through Remind. So clearly I hit the wrong option or something when I did this, that I don't have a chat window up. But if anybody has any questions that they want to just send back to me on Remind, again, if you do @7DFAB to 81010, you can join the Remind group, and I'll just push out one more message to everybody that you can respond to if you have any questions. So this is if you have any questions at all about kinetics and equilibrium, you are welcome to respond to that message. And if you are going to join the Remind group and you didn't do that yet, I'll give you a minute to do that before I resend the message for you to respond to. So in about 3 or 4 minutes, that'll go out. That'll give you a chance to join the Remind group if anybody didn't join it yet and still has some questions. So I'm just going to leave this up here. If you have any questions at all, I'm just going to do this for a second. If you have any questions at all regarding kinetics and equilibrium, please feel free to respond to the message that you get on Remind. And if I don't get any messages in the next couple of minutes, I'll just sign off. Okay, so something just came in and said, from Amanda M, can you go over the change in pressure and change in temperature? And I'm assuming that means that you want to go over it again. So let's say we have 2H2 gas plus O2 gas, and let's say that we're making water as a gas also. So if we want to know about the shifting, and this is an exothermic reaction. So heat will be in the product side. So let's say that we want to talk about what happens with the shifting when we are changing temperature, changing pressure, changing concentrations. So remember that increasing pressure shifts to the side with fewer moles of gas. So if we want to know what happens in this reaction with an increase in pressure, we need to count up the moles of gas on each side. So this is a 2 in front of a gas. This is an understood 1 in front of a gas. So this side has 3 moles of gas, whereas this is a 2 in front of something that's a gas. So this is 2 moles of gas. So in this situation where we have 3 moles of gas and 2 moles of gas, increasing pressure will shift to the side with fewer moles of gas, which in this case is the right-hand side. So shifting to the right. This is according to Le Chatelier's principle. Okay, so when they say, what will happen in terms of the number of moles or in terms of anything, when they add something to a system at equilibrium, this is, when you talk about the shifting, you're talking about in terms of Le Chatelier's principle. So when we increase the pressure and shift to the right, that means that we are going to, as a result, increase the number of moles of water. And as a result, we're going to decrease the amount of H2 and decrease the amount of O2. Now, in terms of temperature, someone asked also about the temperature. Let's see. This was Amanda also, and Caitlin S. We're doing another problem using Le Chatelier's principle. If we increase the temperature, it favors this. We're going to favor endothermic. And if we're going to favor the endothermic, that means it's going to shift to the side where heat is absorbed. So in this case, increasing the temperature will shift to the left because that's how we can absorb the heat and make the heat a reactant and be absorbed and reduce the amount of heat. So Lauren W. said she still doesn't understand the shifting to the left and the right. Hopefully this problem right here just fixed that. And Jack N., your question about why a solid precipitate cannot reach equilibrium. Let me just get something up on the board for that. So let's say we have AgNO3 aqueous plus NaCl aqueous yields AgCl, which is a precipitate on table F, and NaNO3, oops, I'm gonna run out of room, aqueous. These are ions. These are ions because remember, ionic compounds in aqueous solutions make ions. This is also ionic aqueous, so these are separate ions. These ions are connected to each other. The ones that are aqueous, the ions are free to move around in the solution. A precipitate, which is a solid, has the ions connected to each other. Those ions, if they're connected to each other, they're not available to react with the ions that are freely moving in solution. So this is, again, this is for Jake N. Jake, this is the reason why when a precipitate is formed, we have ions that are connected to each other. This is why those precipitates cannot participate in a reverse reaction. When you are talking about solubility, a saturated solution being the rate of dissolving equaling the rate of precipitation, this does not dissolve to a large degree. This does not dissolve to a high enough degree in order to have the ions able to react with the other ions that are present in solution and make the reaction go in both directions. So hopefully that addressed your question there about that. And water as a reactant not being able to maintain equilibrium, it's not when water is a reactant that it can't maintain equilibrium, it's when water is a product. And this would be a similar type of reaction. For example, if we have a titration, neutralization question, where we have HCl plus NaOH making NaCl plus H2O liquid. Again, this is free ions, this is free ions, NaCl is free ions, and in H2O liquid, it's molecules. So the ions are freely moving in the solution. But the water molecules are going to be connected. Okay, so since these H's and O's are connected to each other, they're not free to react with the Na and the Cl to make more NaOH and more HCl. I'm gonna go back to the remind. I'm just gonna go check and see if there's any more messages for me. Another message to you just came out. So I answered Jake's question. Lauren W., we just did 2 more examples of Le Chatelier's principle. Annalisa W., are the rates of reaction always proportional even if stress is added to one side? Okay, so when we look at a reaction, again, that's at equilibrium. Our stress is not added to one side. The stress is added to the system, and the stress affects the reaction going in one direction more than the other. So we don't add heat to the right, we add heat to the system. Remember, this is happening somewhere in a closed container when it's at equilibrium. And so we have H2 gas, we have O2 gas, and we have H2O gas, all in the same container. These molecules are all in the same space. When you add a stress to a reaction, the shifting is based on where they fit in the reactants and the products, but the stress is added to everybody. It's just a matter of the fact that the stress only affects certain reactants, and it doesn't cause other reactants to change their behavior. It's just the result. And I'm going in circles here, but it doesn't actually, so when we increase the amount of H2, we're not adding it to the left-hand side. We're adding it to the container, but the result is that it makes the H2 as a reactant react more and make more water. So we usually think about it in terms of where they fall on the left and the right in the reaction, but we have to remember that they are in a container altogether. Let me just look and see if there's any more messages coming in. I have another message from Caitlin S. Do you know who is doing the 3rd review about phases and phase changes? I don't have that up on my screen right now, but maybe what I'll do is I'll look and see if I can get that link out to you so that we can make sure that you, actually, if you look at the bottom of my, let's see, if you go down and you click on where it says Regents Chemistry Review, Live Stream, Kinetics, and Equilibrium, if you click on that, the link for the other sessions is coming up, and I'll just write it on the board here, HTTPS, oh, that's coming out really sloppy, so let me do it this way. docs.google.com/spreadsheets. No, that didn't do it. Hold on. Yeah, no, I'm having trouble finding that link for you. I thought that I could find that link for you without going off of this screen, but I am unable to do that. So what I will do is find that here on my phone and get that back to you. Because I just sent that out. Actually, what I'm going to do for those of you who are just in the Remind group, I'm just going to push out that next link to you via Remind. And so if you text at 70F to 8:10:10, if you haven't already done that, I am going to sign off now because I don't have any more chemistry questions. So I hope this was helpful. And then as soon as I sign off, I will send the link to the next live stream out to that Remind group that joined. So at 70FAB, even if you're looking at this later in the day, So I'm sorry, if you're looking at this later in the day, don't join the Remind group because this is 9:59 a.m. I'm signing off for 10 a.m. And once I send out that message, this Remind group will no longer be active. I'm actually going to delete the Remind group after I send the last message. But if you have the if you click on the live stream Kinetics and Equilibrium link at the bottom, you should be able to click on the docs.google link there and should get you to the live streaming Regents schedule. So I'll just make sure that that's there. And good luck studying. Hope everyone does great on the Regents. Hopefully this was helpful. And goodbye.